have an exciting announcement today, which is my and Ancha's book actually has been printed. And I got these on Friday. You can see there's a little damage to the bottom here. The UPS person dropped all of them right in front of me when he handed them to me, right on the edge. So fun. And then, yeah, me and Ancha also got these fun ducks. This is known as the duck book. So quack, quack. This is 1 year of our lives. We wrote over 2 reinvents. So we have all the latest content here. We had to wait for the most recent reinvent 2020 December to finish, and finished as quickly as we could afterward. 500 pages, and yeah, covers everything from streaming and Kinesis and Kafka and all kinds of stuff. Yeah, data engineering, data science. It's really, like, quite honestly, I'm super impressed with it. I've actually gone back to this to reference things that I wrote because I could not remember how to do something. Yeah, so Ancha, you've done that too, right? Like, we've been looking something up.
I've done that too, yeah. So suddenly you're working on something and remember, wait a minute, I wrote about how to do this just a few months ago. So I went back into the manuscript and yeah, refreshed my knowledge there as well in my own book.
Yeah, and we're pretty excited. We hit #1 in quite a lot of categories: computer vision, NLP, AI, mathematics somehow sneaked in there. So yeah, pretty exciting stuff. In fact, we even have a small section on quantum, and I'm super excited to see Eric Kessler's talk today. We also are the whole end-to-end use case covers BERT. And building BERT pipelines. And so Nathalie is going to actually, and Connor are going to talk about some advanced techniques to optimize your deep learning models with a technique called pruning. And so I think, yeah, Ancha, I think we can kick it off, right? Is there anything else?
Yeah, no, let's jump right into, I guess, the agenda for today.
Yeah, so the agenda, we'll talk about learning quantum machines. This is a really cool topic. Eric's going to talk about a project called Penny Lane, which is a machine learning focused open source project for quantum computers, and talk a little bit about quantum ML, quantum AI. And then next up, so that'll be about 20 minutes, maybe 25 minutes. Eric, take all the time that you want. Yes, everyone wants to learn about this stuff. And same with Nathalie and Connor. If you guys keep talking, like, we'll keep recording, yeah, even past the hour. So me and Ancha always buffer extra time for this. So that'll be the pruning talk and how to use Amazon SageMaker Debugger specifically to do this deep learning like optimization. So yeah, Eric, why don't you grab the screen share?
Sure, absolutely. I think you need to, oh no, okay, I should be able to do it. Okay. Can you guys see my screen now?
We can.
Yes.
Okay, fantastic. Yeah, I'm super excited to be here today. Ancha and Chris, thank you so much for inviting me. Of course, my talk's probably a little bit out of the usual curriculum here, but I do want to talk about quantum computing, and specifically the intersection between quantum computing and machine learning, because I think there's a lot of interesting things and interesting analogies that are going on at the intersection of these two fields. But before we, sorry, I should introduce myself. My name is Eric Kessler. I am a senior product manager for Amazon Braket, the quantum computing service on AWS. I have a background in quantum computing, but also spent 6 years working on the machine learning side here at AWS, and then came over back to quantum computing and are now product manager on our service. Before we jump into quantum machine learning and the combination of quantum computing and machine learning, let me briefly explain to you, why are people excited about quantum computing in the first place? And the reason is that once we have large-scale quantum computers, there is a broad variety of different use cases people can solve using quantum computers, from cryptography over physics and chemistry, wherever you need to simulate the properties of a natural system that is behaved by the laws of quantum mechanics. For example, in the area of nitrogen fixation, when you want to produce fertilizer, you want to understand the properties of that process. There's this famous problem around FeMoco, which is a particular molecule that helps in the synthesization of nitrogen, which is used in agriculture for fertilization and so on. And understanding the properties of this process, of these molecules and so on, that is something that very naturally lends itself to quantum computing. Material science, for example, in terms of high TC superconductivity, but also in optimization and machine learning, obviously, are many interesting problems. And the thing that is, I think, very important is that we're not talking about making things a little bit faster, but it's really a foundational change in the way we do things. Practically, we will be able, once we have large-scale quantum computers, to do things that we physically are not able to do today. For example, simulating these large molecules, which today is only possible with very crude approximations. And it would really be a very transformational technology once we have access to these large-scale devices, and will change how we do things, for example, in chemistry, how we do things in material science, and will allow us for the first time really to a priori calculate properties of materials and design materials from the get-go without a large experimental trial and error approach. But of course, there's a big catch here, namely that we're still far, far away from having large-scale quantum computers as the ones we would need for these applications that we know, that we're familiar with. So when you look at this graph here, we have on the y-axis the error rates, so how clean are our qubits that we use, and on the bottom we have the number of qubits that we have available. We see in this region, this blue region over here, this is where the algorithms are that we know, that are transformational, that will allow us to do really new things. But unfortunately, we're over here. So we're still at the boundary from where the green area, where we know we cannot do anything because these devices that are in this regime, they're simulatable classically. So we can just take a classical computer and simulate them. So there's nothing we can do new with those devices. But we're about to cross over into this middle area, this big area where these devices can do fundamentally new things. So we cannot simulate these devices anymore with a classical computer. But on the other hand, we also don't know what to do with them. We don't have algorithms that we know that we can use. So this will be an era of quantum computing that is dominated by experimentation and people trying to find new types of algorithms that you can potentially apply in this regime. So, and this is also the topic of the talk. So we're going to talk about this region that is labeled with the number 2. Before we dive into that, I want to start with what we're not going to do. So I'm not going to tell you about how a qubit is the generalization of a classical bit and that it can live in what's called superposition, so being in 2 states at the same time. We're also not going to discuss how quantum circuits are the generalization of Boolean circuits and how you can take these elementary building blocks to bottom-up construct quantum algorithms that we, as we've seen on the previous slide, can use for different applications. We're also not going to talk about how entanglement is really in a very foundational sense at the bottom of the computational power of these algorithms, and how entanglement can be linked back to how quantum computers solve these problems. We are definitely not going to talk about how you build a quantum computer, for example, by literally taking individual atoms and trapping them in electromagnetic fields and poking them around with laser beams, or by taking superconducting materials on a chip where then the electrons behave as a collective and without resistance encode quantum information, or alternatively, how we can use photons, light, to do quantum computations, or even take individual atoms and arrange them in arbitrary 3D configurations like this Eiffel Tower visualizations here, and even do computations in 3 dimensions. So definitely, we're not going to talk about any of this. Instead, what we're going to do is to take a top-down view, right? So we're putting everything in a black box, and see what we can do with these devices. So let's say I have this device, which I call a QPU, a quantum processing unit. And I'm going to explain that in an analogy side by side with, say, a GPU. Yeah. So this QPU device can execute certain programs. These programs we call circuits, just like a GPU, for example, can do neural network calculations. Okay. For neural networks, we know they have free parameters, for example, the weights, or a special type of free parameter, which is the data that I can bring into the neural network. So I can fill that free parameter with the data, I can fill free parameter with the weights that I have. Just in the same way, our quantum circuit has free parameters. So I can attach weights to the individual gates in a quantum circuit. And then what does this device do? Well, it computes something, computes a function that then depends on those parameters. And in the classical case, that function depends on the weights. It also depends on the data that we put in. But if we want to, so in the quantum case, that is enough, right? We can, in neural network learning, the problem that we want to solve is to find the function that best fit our data. Since we can apply quantum computing for optimization or for computational chemistry, we can encode the problem that we want to solve in the structure of that circuit itself. But I can also use quantum computers to solve machine learning problems. So I can choose to take also data as an input to the quantum circuit. And then the analogy is really one-to-one. And like in machine learning, we take now this objective function that we've computed on this device, and we iteratively adjust these parameters to converge to a solution to the problem that we had. As I mentioned before, it could be that we encoded an optimization problem in that circuit. It could be that it's really a machine learning task that we want to solve. And this is what people call variational quantum algorithms. And it's the dominant form in this intermediate, or what's called NISQ era of quantum computing, until we're at the place where we have full-scale quantum computers. And the goal essentially is to utilize to whatever the device can run, right? And since we don't know how to build bottom-up programs or quantum circuits with low qubit counts and with low depth, we borrow this very powerful idea where we actually don't program the circuit directly. Instead, we prescribe this general circuit architecture and let a classical algorithm iteratively find the best circuit within those bounds for our problem. And it's hard to overstate the magnitude of this parameter shift in quantum computing. This paradigm shift, parameter shift, I'm already going to the next slide here. Because the quantum computing community is coming from a very heavily theoretical dominated field, right? In the early days of quantum computing, people were extremely focused on the computational complexity, on what is the computational power of these devices. Prefactors don't matter so much. It's all about the scaling. There were only a handful of algorithms that were known, and those were theoretically very well understood. Well, now with these variational algorithms, the situation is exactly the opposite. We have now a class of algorithms where we know very little theoretically. It's entirely driven by heuristics. There are lots of variations, which optimizer you use, what ansatz, what kind of architecture for your circuit, and so on and so forth. And in many ways, the answers to the question, will it work? How well will it work? What optimizer should I use? And so on and so forth. In many cases, the answer is, we don't know, let's just build it and find out. So there's a massive change in mindset, but luckily, this is not the first time that we're seeing such a shift, right? Because when you think about it, the field of machine learning went through a very similar evolution. And in many ways, quantum computing is in a very similar situation that machine learning was many decades ago, right? As we already discussed, the algorithms are almost exactly the same when you replace a quantum circuit with a neural network. And what I said before, that every variational quantum algorithm is based on this idea of let the algorithm find the best circuit within some bounds. Well, machine learning or neural networks do exactly the same, right? The architecture of your neural network are the bounds within which the algorithm, the classical algorithm, can find the best model that fits your data. Yeah. And also in machine learning, still today, we can't really theoretically prove that a neural network can recommend to you the next book that you want to read, or can help a drone navigate around obstacles, or all the amazing applications that we have for machine learning today. We know very little about those theoretically. But the machine learning community fully leaned into what I call this kind of adoption-led innovation, right? Somewhere I read this kind of analogy that working in machine learning is like being an architect in an ancient society that hasn't developed the science of static yet, right? So you want to build a bridge and it keeps collapsing, and somebody invents the concept of a pillar, and then pillars are all the rage. Everybody builds pillar, but we don't know if there is an even smarter design like a hanging bridge that would allow us to build much bigger bridges. We just have to try and see if it works, right? So in machine learning, really for decades now, it has been this paradigm of theory follows experiment, right? So experiments and experimental results, empirical results, are way ahead of our theoretical understanding in machine learning. And you know, as you probably know better than I do, but today we still don't really understand why deep learning models train so well, despite having highly non-convex objective functions, many local minima, and so on and so forth, right? So this idea of build and try, and for better or for worse, quantum computing will probably follow that path over the next years while we are in this intermediate regime. Because it is just extremely difficult to prove anything useful from a theoretical starting point about these heuristical approaches, about these variational approaches. The best way is just to build these devices and try out ideas. And I'm sure there will be many cool surprises for us and many new ideas, and a lot of interesting things are going to happen. There are obviously also other parallels between these two fields, right? So we're going to talk a little bit about kind of the differentiable programming, how backpropagation helped us really machine learning to success. And also obviously the access to really mature, intuitive end user libraries that make it easy to train, build, and deploy these models on the machine learning side. So let's dive a little bit deeper into this analogy, because as I said, machine learning underwent a very similar evolution to what we're seeing in quantum computing now. Think back to the 50s when the first perceptron models were proposed, right? Perceptron, what we'd call today kind of a one-layer feed-forward network, I guess. The focus at that time was very much on the theoretical understanding of the computational power of these systems, right? There was no hardware to run these models on. I think the first perceptron was run on a special purpose hardware that was built only for that for that purpose back in the 60s or so. And like in variational quantum computing today, it was extremely hard to say anything about the computational power, right? People tried and they failed. So that led to, you know, what you all are very familiar with, the kind of first AI winter starting in the 70s here. Until then, in the 80s, people rediscovered the backpropagation algorithm that was applied to neural networks. I think most famously in the work from Jan LeCun, where he used that for training larger scale convolutional networks that he showed can be trained now with this backpropagation idea. Yeah? But even that wasn't enough for widespread adoption of machine learning or neural networks specifically. Yeah? We can, of course, debate where this point of what's labeled here on the chart, the deep learning revolution, where that exact point is. But for argument's sake, it still took at least 2 decades until that happened. So what was missing? Yeah? I'd argue it's essentially 3 pillars that helped neural networks be widely adopted in industry, right? So first of all, hardware and data become widely accessible to a lot of different people from different fields, different researchers for different use cases. The open source tooling made applications of the algorithms like backpropagation really easy and intuitive, and without needing to know all the intricate details of the backpropagation algorithm, you could just use it out of the box. And then third, there started to be a diverse community. When neural networks came out of the lab and into industry, people started exploring neural networks for all sorts of use cases. The use cases evolved. It used to be that neural networks were designed specifically around voice recognition and image recognition, natural language processing, and so on. But as you all know, neural networks are being applied everywhere today, from recommendation engines to forecasting and whatnot. So there's really a new momentum that came into the field when these techniques hit industry, and a broad community of developers and researchers were able to play with those algorithms. And without sounding too grandiose, but in a sense that is exactly what we're trying to do with Amazon Braket, right? So Amazon Braket is a quantum computing service on AWS. I'm going to go into a little bit more detail later on. But the goal is to make quantum computers and quantum computing technologies accessible on demand for everybody. There's no upfront commitment. Like any other AWS service, you log in, you pay for what you use, and you build these models where your data is. Yeah. The open source tooling, we are working very close together with an open source library that is called PennyLane. We recently joined the steering council. We're working with the team to build better tooling around how to train these variational quantum algorithms. And PennyLane is kind of cool because it actually allows you to use existing machine learning tooling to build differentiable quantum programs, to build variational algorithms. So you can literally use TensorFlow or PyTorch, for example, to build these quantum algorithms. So it's an excellent entry point for people with machine learning experience to start experimenting and playing around with early quantum computing prototypes and quantum computing algorithms. And of course, it's community driven, open to everybody, and we encourage everybody to start learning and contributing back to the library. So it's an exciting project. And then finally, we want to bring quantum computing out of the lab. That's why we launched this service, right? So we want to connect to domain experts. We want to learn. We want to bring researchers together with experts from industry to learn about use cases where really the pain points, so that we are not focused on the algorithms that we know, but we will learn about new problems that we didn't have on the radar, perhaps. And specifically, also to bridge the gap between machine learning and quantum computing, right? Because both of these communities can learn a lot from each other, in my opinion. And obviously, that's a topic that's very near to my heart, in a sense, right? Because I have a background in quantum computing, but I worked for a long time in machine learning. And I can really say that both of the communities, I'm extremely impressed, right? So on the machine learning side, this attitude about this builder attitude and the willingness to experiment and fail and just use whatever is available to make things work. And I spent a lot of time in quantum computing as well, and I met some of the smartest people I know in that community, and I continue to be very impressed by all the amazing scientific results that are coming out of this field. Yeah, and so with PennyLane and Amazon Braket, we want, on the one hand, specifically with PennyLane, make quantum computing accessible for people with a machine learning background, because we think there's so much to learn for the quantum computing community in terms of, how do we find the best optimizers? How do we really design these algorithms, and vice versa, by providing for the quantum computing community mature machine learning tooling that has been developed, and we can apply these same toolings and the same ideas to quantum computing to accelerate the innovation in that field. No. So I'm gonna just spend a little bit of time. I think I'm already running up against the clock here, but I want to spend a little bit of time double-clicking on this analogy between backpropagation and what we do in quantum computing, because I think it's interesting and also illustrates a little bit where the problems lie today. So you all are familiar with kind of this idea, right? So how do we train neural networks? Well, again, we put data and weights, we get some objective function, and then there's some backpropagation magic that happens. I don't want to go into the details there, but the bottom line is the backpropagation algorithms allows us to analytically and efficiently compute the gradient of this function. Yeah, and that's it, right? So we use the gradient of that function to update our parameters. and then we continue this cycle. And the very same is true in quantum computing. And again, we can choose to have data here or not. And it's exactly the same picture. And there's one approach to calculate this gradient in quantum computing as well. It's called the parameter shift rule that allows us to compute this gradient. And it looks very much like the finite difference formula, but it's not. There's actually an exact formula here with a few free parameters that allow us to efficiently compute this gradient. Yeah. But I should mention at this point, right, this is one approach. This parameter shift rule is one of the earliest approaches that was developed to calculate quantum gradients. And it's by no means clear that this is what's going to prevail, right? In machine learning, we know the backpropagation algorithm is the method of choice, and that's what people use, and that's how you calculate gradients. Here in quantum computing, all of these questions are still day one. Yeah? So we know there are different approaches. There are ways to approximate gradients that are very well suited to the strength of quantum computers, more robust to noise. So there's a lot of experimentation that goes into this. And frankly, until we have larger scale devices, these will probably remain open questions. But that's what makes it so interesting, because people are researching these fundamental concepts and trying to understand better how to optimize these algorithms in the specific energy landscapes that you get, which have their own features, right? So when you remember of the vanishing gradients in deep learning, we have this phenomena of barren plateaus that is kind of the same, similar ideas, similar challenges that makes it hard to train these algorithms. Yeah? So there's a lot of research to be done and a lot of analogies to be drawn between the two fields. Okay, so with that background, I want to show you how you can get started, right? So let me introduce you again to Amazon Braket. So Amazon Braket is our quantum computing service on AWS. In this spirit of the analogy between machine learning and quantum computing, we're thinking a lot about Amazon Braket in the context of Amazon SageMaker, and you will certainly see certain ideas that are reflected and that are mirrored from SageMaker. We're working very closely with the SageMaker team on the components that are aligned between the two fields as well. So here also we have 3 components of Amazon Braket. We have fully managed development environments that are based actually on SageMaker notebooks, as a matter of fact, that come pre-installed with different quantum computing libraries, make it easy to get started, different tutorials, and so on. We provide fully managed circuit simulators. Yeah, so keep in mind, quantum computers are still scarce. They're not an elastic resource like you're used to it from AWS. And it is much more cost effective while you prototype, while you build, to test your algorithms against classical computers that emulate the behavior of a quantum computer. Yeah, and so that's we provide here with the circuit simulators. But then most importantly, we also provide secure and fully managed secure and on-demand access to different types of quantum computers to help you, test out different approaches, test different devices, get access to this technology. So today on Amazon Braket, we have 3 different types of quantum computers available. So this is what's called a quantum annealer from D-Wave. We have a quantum computer based on trapped ion technology from IonQ, and we have a quantum computer based on superconducting technology from Rigetti. And all of those devices are available on demand on AWS. Everybody can just log into the AWS console, search for Braket, and you will see those devices, and you can get up and running within a couple of minutes and try your first circuit. Yeah. As I mentioned before, we also have different types of circuit simulators that help you test your algorithms, fine-tune, do hyperparameter optimization, and things like that. From kind of the lightweight debugging solution that comes shipped with our SDK to high-performance managed simulators that allow you to run larger circuits in the cloud and scale out into the cloud. So with that, I'll just show you the last slide, how you get started. As I mentioned before, just navigate to your AWS console, go to Amazon Braket, and you can get started in a couple of minutes. I also want to point out our GitHub repo, which has different examples, how to get started with Amazon brackets, specifically also in the context of penny lane and different variational algorithms. I also can highly recommend going to pennylane.ai. There are lots of nice tutorials on that webpage. All of these examples you can run also on Amazon bracket. Yeah, it's easy to get started. And with that, I think I'm gonna wrap up and to leave a couple of minutes for questions.
Yes, thank you so much, Eric. That was really insightful. I always enjoy learning a little bit more about quantum technologies. Let's see, everyone, if you have questions for Eric, please put them in either the Slack channel, or if you haven't joined the Slack channel yet, here in the Zoom Q&A. I do have one question here coming in for you, Eric, so I'm just going to read it out. Someone is asking, what are the benefits of shifting from the classical machine learning to the quantum penny lane service, etc.? And how do you compare the regular AWS machine learning services with these ones, rather than in direct comparison to bracket?
Yeah, absolutely. No, this is a great question. So first of all, I want to point out that penny lane can not only be used for using quantum computers for machine learning tasks, but also these other application areas in quantum computing, like optimization, like computational chemistry. Those can be directly formulated in penny lane. So there's always the idea of, using quantum computers to solve a machine learning task. And I'll talk about that in a little bit. But more broadly, I think my point here is that even if we don't try to solve a machine learning task, even if we want to solve a problem in computational chemistry, the way that we know how to solve these today with the devices that are available make these quantum algorithms look like machine learning models. Yeah. So that as a meta point. In terms of applying quantum computers to problems in machine learning, it's a very early field of research, I would say. So there are some theoretical results that show that certain kernel methods can be sped up with quantum computers. So there's a theoretical result that shows if you have a full-scale quantum computer, kernel methods can be much faster on a quantum computer. There are also some early results that show if you want to build a machine learning model to predict anything on distributions that are quantum in nature, and I'll come back to that, what that means, you have a much higher expressiveness of your model. You can build much smaller models and actually fit the data much better. So what are distributions that are quantum in nature? So think about if you want to build a machine learning model that predicts kind of configurations of atoms in a molecule. Yeah. So this will be a distribution, a probability distribution that is quantum in nature. And it can show that this is very hard to represent with a classical neural network model. So if you had a quantum computer and you could build a QNN, a quantum neural network, you have a higher expressiveness and you could do that more efficiently and better. So there are kind of niche applications for using quantum computers to do actual machine learning tasks. But generally speaking, it's an early field, and there's a lot to be researched, quite frankly.
All right. Next question coming in. Can you comment how our work or your work is comparing to, and I hope I pronounce it correctly, the Qiskit SDK from, I think that's IBM's efforts, right? That's right. So Qiskit is a programming framework for quantum computers. Is very well respected in the community. Is a nice library. I compare it a little bit with the world of machine learning again. So you have TensorFlow, you have PyTorch, you have MXNet. And so different people have different preferences. Ultimately, we're all trying to do the same thing, but there are certain different philosophies. Qiskit has certainly done a great job in terms of community building. Obviously, IBM has worked with public quantum computers for a long time.
And yeah, I think we think there's different philosophies, different approaches, and ultimately within Amazon Bracket, we listen to what our customers want to do. Just like SageMaker, you can use different frameworks, and we listen to our customers what they want to write their quantum programs in, and that's what we will support in the future.
All right, sounds good. And yeah, I mean, if you stick around a little bit longer, if you have a couple of minutes, Eric, and maybe just see if there's a few more questions coming in, you can answer. And I guess in the interest of time, we move forward. I kind of started to see if people have a good quantum joke. I came recently across a couple of those on the internet. So let me ask you maybe one, Eric, and I probably pronounced the name wrong again. So why is Hadamard never invited to quantum computing lab parties?
I don't know.
Because he turns everyone so negative.
Nice. That's great.
All right. Thanks so much, Eric. And I'm super excited to introduce our next speakers, Nathalie and Connor. And Connor, I think you're gonna start with the part. So why don't you just start sharing and briefly introduce yourself, and then also Nathalie. Super excited to have you here. And you're gonna tell us, I heard, about how to use SageMaker Debugger to gain more insights into your model training, and specifically how to save costs by pruning state-of-the-art deep learning models. So super excited to hear what's going on there. Over to you, Connor.
Absolutely. Thanks so much, Antje. So hi, everyone. My name is Connor Goggins. I'm a software engineer on the SageMaker Debugger team in AWS AI. I'm here with my colleague, Nathalie. So basically today, I'll be walking you through an overview of what model pruning is, explaining why it's becoming increasingly important for the training, inference, and deployment of machine learning models. And then Nathalie will show you her demo of iterative model pruning using SageMaker Debugger that illustrates how our team's product can be applied to effectively reduce the size of models, decreasing deployment costs and inference times while preserving accuracy. So let's get started. Okay, so to begin, let's look at the current state of the art in computer vision and natural language processing. So right now, the most sophisticated image classification models contain, at the very least, tens of millions of trainable parameters. And the best language models contain easily hundreds of billions and now recently even trillions of parameters. So if you note on this chart, actually the y-axis is on a logarithmic scale. If it were on a linear scale, none of the pre-2020 models would be visible at all because the size of optimal models has increased so dramatically in just the past year and a half. And as a result, training these massive models is highly computationally intensive, which makes it a significantly expensive process, not only in terms of money, but also in terms of time. Additionally, the highly significant size of modern machine learning models often makes things like deploying to edge devices or achieving fast inference times very challenging. So with all of these factors in mind, scientists are beginning to look into ways of reducing the size of models in order to reduce training costs, deployment costs, and inference times. So right now, the three most popular techniques for reducing model size are quantization, knowledge distillation, and model pruning. So first, quantization is the act of converting the data types of model inputs and weights into smaller types with the ultimate goal of using less memory and making calculations faster. So one example of this might be if you're working with a network of using input data and parameters of 32-bit float data types, you could quantize it down to one that uses 8-bit integers instead. So, you know, on one hand, you've got the 4 times smaller data type size. And then on the other hand, you've got the additional benefit of the fact that 8-bit integer math is generally simpler and faster than 32-bit float calculations. And the reason the SageMaker debugger team doesn't focus on this type of compression is because approximating the parameters using smaller data types in this way ultimately ends up sacrificing precision for a compressed representation. Research has basically shown that there's often a direct relationship between the reduction in model size and a commensurate reduction in accuracy using this technique, which is why we steer clear of it. The second popular technique is knowledge distillation, which involves training a much smaller student model to approximate the predictions of a much larger trained model. So using the teacher-student architecture. Although this strategy has seen some success, especially when dealing with ultra-large language models like BERT, we don't actually focus on this technique either because it still requires training the complex large model in the first place in order to gain the refined representation. So although inference might be cheaper, the training process becomes more expensive because now you're training two separate models, even though you only end up using one. So that brings us to the third and final model compression technique, which is model pruning, the primary focus of the talk. So what is model pruning and how does it work? Model pruning at the very highest level of abstraction is the act of identifying and removing redundant parameters in a machine learning model, which, if done correctly, ends up resulting in a smaller model size, faster training times, and faster inference times while preserving accuracy. So we're focused on a variant of this called iterative pruning, which involves regularly removing weights over the course of the training process. So how is this possible? The primary insight behind the feasibility of model pruning is that all the millions of weights in the best machine learning models, they're not all equally important during training and inference. Really, only certain parameters in the model are critical to obtaining accurate predictions, while others are significantly less relevant and can be pruned or removed. So for example, on this slide, you can see a heat map of activations for what's basically a small image classification model trained on the MNIST dataset. The yellow and pink colors in the model graph indicate neurons with high activations, while the blue shades indicate neurons with lower or quasi non-existent activations. And you can see that many of the parameters in the model are pretty consistently blue, indicating that they aren't being effectively leveraged for classification purposes and can be pruned to achieve smaller model size with faster training and inference times while preserving the accuracy of the overall model on the image classification task. So there are several different types of iterative model pruning. One is something called non-structured weight pruning, which analyzes the model, determines the lowest and therefore least relevant individual weights, and then removes them from the model graph, resulting in fewer connections overall. That's a diagram of a basic idea of how this works. And then another technique, which we'll see Nathalie apply in her demo shortly, and which is particularly relevant to computer vision models, is structured pruning, which involves removing groups of weight connections, such as entire filters and channels. In this case, the technique is going to be applied to convolutional layers. So these gray boxes on the image of the number 7 are visualizations of filters, which process the input from the section of the image that they include into a feature map. So in practice, there are going to be many of these filters applied to this input as the kernel convolves as part of the convolutional neural network process over the input. So we can identify the filter out of these gray filters that has the least significance. So let's say it's this golden filter here, and then remove it from the model entirely. So in one step, we've removed 1 times the kernel width. Remember, that's the width of that square there, even though that's just a filter, and then times the kernel height parameters. So a much bigger reduction than just the removal of those individual connections at a time, as we saw with the non-structured weight pruning. So this is much more efficient. So we have a variety of techniques for determining the significance of these filters in order to prune them down the line, including finding the minimum weight out of all of the filters' weights, finding the average activation, and then also finally finding the product of the activation output and its corresponding gradient in the cost function. And this final strategy, which is probably the most sophisticated out of all of these, is what Nathalie will use in the demo. Given the high performance and particularly exciting applications of large language models, I also want to discuss strategies for pruning sequence models. As you might guess, the architecture of these transformers is completely different from the convolutional neural network architecture of the model that we just applied structured pruning to. And consequently, you really need an entirely new approach to achieve structured pruning on these types of models. If we look at BERT as sort of a representative example of these, popular massively large language models, one of the primary innovations of the model architecture is this concept called attention. So the attention mechanism allows the BERT model to alter the weights of input features directly based on their importance to the unsupervised learning objective used during training. So that might be filling in words on a masked sentence or any number of tasks used for the unsupervised training process. And this concept of attention also supports establishing relationships between input features. So at a high level, the way this is done is by processing the embeddings for each element in the input sequence. So this would be, either a word token or a subword token in a sentence or many sequential sentences that we're passing to the model. And then calculating a matrix of attention weights to determine the relevance of each element in the sequence to each of the other elements. And then finally generating a new sequence of embeddings by calculating a weighted average of the original embeddings using the attention weights. So in doing so, the model produces a sequence of context-sensitive embeddings that accurately preserve not only the meanings of the individual words in the sequence, but also their meanings within the context of the overall sequence. So you can imagine this is particularly relevant with language because context is everything. The word can, for example, might mean any number of things based on the context that it's in. For example, like I can do this, or I ate food out of a can. It's completely different. The BERT model basically includes many modules for evaluating attention, which are independently applied to the same input sequences or stacked on top of other attention layers to learn a wider variety of contextual relationships. And these attention modules are called heads. So while attention as a whole is critical to the functionality of BERT, many heads in the model can actually be removed or pruned without damaging the overall performance. So that leaves us with the task of identifying the least important heads in the model so that we can prune them. And as with the filters in the structured pruning example, there are several ways of determining the significance of heads in a BERT model for subsequent pruning. This includes first finding the minimum, maximum, or average weight in each head, pretty traditional metric, calculating the confidence of each head, which essentially involves taking the average of the maximum attention weights for each head applied to a set of sample sequences, and then also layer-wise relevance propagation, which is somewhat complex, but essentially allows us to measure the intra-model relevance of groups of neurons. Okay, so now Nathalie will present the design of her iterative structured pruning demo using SageMaker Debugger, and then walk through her example notebook applying this system to a ResNet model.
Thanks, Connor, for providing the overview about model pruning. And yeah, as Connor mentioned, I will now take over and show the demo notebook. Can everyone see my screen? Okay, perfect. So before I jump into the notebook, I would like just to give a brief overview of the workflow that I'm going to show. Sorry. So first of all, when you run your training on SageMaker, then the training will run in a SageMaker training container. And in the iterative model pruning workflow, we will use SageMaker Debugger to automatically capture the weights from our models and some additional tensors that we will use to compute filter ranks. As Connor described, once we know the filter rank, we can remove entire filters and the corresponding feature maps from the model. these tensors are automatically stored in our Amazon S3 training bucket. So once the training finished, we can start collecting those tensors, compute the filter ranks. Once we know what are the smallest filters in our model, we can remove them from the model, specify a new model architecture with that basically has pruned weights, and we also set the latest version of the weights in the model. And then we basically start a new training job and just repeat the process, and that's why it's called iterative model pruning. In each iteration, we will remove a certain percentage of our weights. And every time we remove weights, it may happen that your model kind of loses accuracy. So we let the model fine-tune for a couple of epochs because it allows our model to regain accuracy. And by doing that, our model becomes smaller and smaller over time, but we can keep the accuracy kind of, let's say, stable. But there is a point in time when our model will have a too low capacity, where basically the accuracy will drop a lot. Before I jump into the notebook, let me just show you what actually Amazon SageMaker Debugger is and why we use that in our demo. So Amazon SageMaker Debugger is a feature of Amazon SageMaker that allows you to automatically capture tensors from your model training. When you start your training on SageMaker, you just have to specify the kind of tensors you want to have emitted, tensors such as weights and gradients, and Debugger will take care of the rest. So as a user, you do not have to modify anything in your training script nor in your model. But Debugger has some additional features. For instance, you can do real-time profiling to identify performance-related issues in your model, such as resource underutilization. You can monitor system utilization. We also have a whole set of rules for Debugger. So when you start your SageMaker training, you can enable Debugger built-in rules that can identify issues such as vanishing gradients, overfitting, underfitting. And you can also use Debugger for just real-time monitoring, so getting real-time insights into your model. So while the training is in progress, you can already fetch tensors and visualize and see what's happening at each different layer in the model. In the notebook that I'm going to show you soon, we will leverage the SMDebug API. SMDebug is the open source library of SageMaker Debugger that allows you to access, query, and filter the tensors that were recorded by Debugger. And I just would like to give you a brief overview of how this API looks like. So when you run your training on Amazon SageMaker, you just specify now collections of data you want to have collected. You can specify Debugger hook config, and then I select here a default collection weights. That's basically already predefined by SageMaker Debugger. And further, I can also define my own custom collection. Here I specify Relo activation. And this custom collection I will use later on in the notebook to compute filter ranks. And once your training is running, you can use the SMDebug API to now access the data. So first, you use the function create try, you point it to where the data is located, and then you can start iterating over all the tensors that were recorded by SageMaker Debugger. And with try.tensor, you access tensors at a specific step, and it's retrieved as a NumPy array. So you can use tools such as Matplotlib, SciPy, NumPy to access, to analyze and visualize the data. So with just a few lines of code, I can now visualize the activation outputs of my first convolutional layer in real time as the training is still in progress. So I see here the different step numbers. So with that, let's now go into the notebook. Okay. So in this notebook, what I'm going to do is I will apply this iterative model pruning workflow now on a ResNet 80 model from the PyTorch model tool. I'm taking a pre-trained model, and here we can see the architecture of the model. So ResNet models, they consist of several basic blocks, where each basic block consists of convolutional layers followed by batch norm and Relo activation. In the first step, because I'm fine-tuning the model on a new data set, it's the Calltech 101 data set, which has 101 classes. I adjust now the final layer of my model to only output 101 image classes. Then I just save the model definition with the weights. In the iterative model pruning, I will use SageMaker experiments to track all the different training jobs that I'm running, so that I can later on use SageMaker Studio to visualize my pruning experiment. And in order to create a SageMaker experiment, you just use the SM experiments library, and then the function experiment create there, you just have to pass in the name. So now let's take a look at the model pruning step by step. Every time when I create a new training job, I want it to be associated with a new trial. A trial is basically a trial within a SageMaker experiment. Next, I define the debugger hook configuration that I have shown you before in the slides. I collect here now all the weights from the model, as well as the activation outputs. And because my ResNet model consists of batch norm layers, I also collect the running mean and variances, because later on, when I prune the model, I also have to adjust those tensors. You can then also specify how often you want to have this data collected. In my case, I specify now 100 iterations, so every 100 step, I will have those tensors collected by debugger. Now I'm ready to start the training. So in SageMaker, you can use the estimator API. In my case, I'm training a PyTorch model, so I'm using the PyTorch estimator API. My training is defined in the train.py file. And now I only have to specify the debugger hook configuration. Before I start the training, I define the experiment config. That's basically a dictionary that just specifies the name of the experiment as well as the name of the trial. And I pass it into my estimator fit function. So when I start a SageMaker training, SageMaker can now associate this training job with that specific experiment and the trial. And debugger will now automatically ensure that the tensors that are specified in my custom collection will be automatically collected. So after the training is finished, I will now access the tensors to compute a filter ranks. And just brief iteration on what Connor already described. So what we do in filter pruning is, when you define a convolutional layer, you have to specify the number of input channels, the output channels, and the kernel size. In our case, we only have one input channel because it's a grayscale image. The kernel size defines the width and the height of the kernel. And a filter is basically a set of kernels. And typically in a model, in a convolutional layer, you're not just having like one filter, but typically you use multiple filters that produce multiple feature maps. So how can we now compute a filter rank? What we do, we use now the SMDebug API. We have the trial object, and we iterate over all the steps that debugger recorded. And we strike the tensor and we iterate over all the activation layers in the model, as well as the gradients. And these are the tensors we are going to use to compute the filter rank. So we build here the product and then average it across all the other dimensions of the tensor so that we get one scalar value. And we compute these ranks for all the layers in the model. Here we normalize them between 0 and 1, and then we can sort the filters. I have here a helper function that will just return for each filter in my model a value so that I know whether it's an irrelevant filter or not. So what the function outputs is the list is the 100 smallest filters. So let's take a look on the first entry. It tells me that in the fourth layer of my ResNet 18 model, that the 272nd filter had the smallest value. And I get now this giant list, and I can use this information to prune the model. I have a helper function that basically will just go through all the layers in the model and identify if the current layer has a filter that can be removed, and will then update the model definition. So for instance, it tells me here that the first layer of the ResNet 18 model, the number of filters has been reduced from 64 to 63. So the output of this function is now a pruned model. And I can now start the next pruning iteration. So that's basically an overview of the workflow that I already shown in the presentation. And we can now take all these code pieces together and run them in one big for loop. And every time I will create like a new trial object in the SageMaker experiment, so I can now go to my SageMaker experiment view in SageMaker Studio. So you can select the experiment and the trials. Then you will see here the experiments that have been created, and then there's in each experiment the different trials. You can then open it in the experiment view. Let's take a look. So here I run the model pruning across 12 different iterations. And for each of the training jobs, I collected some additional metrics, such as the accuracy of the model, as well as the number of parameters here. So what we see, so each row is basically represents one training job that I run. And in each iteration, I have a smaller model. So my initial training job ran on the non-pruned version. So it had around 11 million parameters. And then in the end, after 12 pruning iterations, my model only had 750,000 parameters left. At the same time, I can now track also the accuracy. And I see here that it's always like above 80%, but at some point in time, it drops a lot. In SageMaker Studio, can now also create visualizations. So here we see here that my model started with 11 million parameters. The accuracy is always above like 80%, and then when it's going below 2 million parameters, and basically prune the model too much, and it has too low capacity for a given data set it's trained on. So basically the accuracy drops a lot. And I run this iterative model pruning workflow on different kind of models. And the animation that I'm showing here is an example that where I run the model pruning workflow on AlexNet model. And we see here the architecture of the model and the different layers. And here the number of total parameters, and here the different pruning iterations. So what you will typically see is that the initial layers of the model will not be pruned as much as the last layers of the model, because the last layers are typically learning more redundant features, so they will have more lower, smaller filters, while the initial layers commonly learn very important features of your data set. And yeah, so typically you will see that the last layers will have higher pruning ratios. So that's the workflow I wanted to show you. And yeah, if you have any questions, feel free to ask.
Yes, thanks so much, Nathalie and Connor. Great presentation. And we do have questions here. So the first one is around the cost of using or performing pruning, right? So does pruning, for example, increase the error rate?
Yeah, so the idea of iterative model pruning is that we want to remove only the weights that are irrelevant. So the idea is you keep the accuracy relatively stable, but of course, if you prune it too much, then you will sacrifice accuracy. And that is basically when you would want to stop the experiment and just do not run any more pruning iterations.
All right, and another question around the framework support. So one person asked, is it working with TensorFlow layers as well?
Yeah, the POC that I have shown only works for PyTorch at the moment and for ResNet models.
All right, and one question around a general understanding, why would we do the pruning? So the question is, why would you just not pre-process with principal component analysis, PCA and SVD, to reduce the parameters and the feature store? Is it faster to run through the deep learning network to do this pruning? So a little bit more around the reasoning there.
I'm not sure I fully understand the question, but I think what what is referred to with PCA and principal component analysis. Probably you want to reduce the number of input features, so reduce your data set. But in our case, we want to make the model smaller. And having a smaller model is especially relevant if you want to deploy, for instance, to an edge device. You may have memory constraints and other resource constraints. And iterative model pruning helps you to basically adjust these big models to your specific use case and run a smaller version that provides you the same accuracy. But then you have more deployment opportunities, so you can deploy it on edge devices, which the non-pruned version maybe would not work for.
All right, and I hope that answers the question. Otherwise, please feel free to do a follow-up here. One more, you're talking about the iterative pruning, and I wonder if there's another type of pruning, other types, and why you chose the iterative in that case.
Yeah, there is what is called one-shot pruning, where basically you don't do it in an iterative way, but you only have like basically one iteration. But yeah, why we choose this technique is basically in the literature and in the research papers, the state of the art is currently these iterative pruning techniques, and that's why we use the same.
All right, I think that covers the questions I see here. Here's one more coming in. Correlation is not taken into account for pruning. Am I following? Yeah, he's following up on PCA. So correlation, is that the question clear to you, Nathalie? I don't know.
I mean, you're not taking correlation into account for the pruning.
Yeah. Yes, I think the questions are like typically when we're reducing things in classical machine learning, we always think of SVD and PCA. And so I think there's a little bit of confusion here about what we're trying to reduce. And so one thing to point out is that this is happening during training, right, Nathalie?
Yes, exactly.
Whereas those other techniques are typically applied before training to make the training go faster. So I think that's the core difference. Yeah, Ancha, there's one more good question here about distillation on Slack.
Yeah, I just saw that coming in. Yeah, pointing to the beginning of the session, Connor, when you mentioned the platform does not support knowledge distillation because of the need to first train the large teacher model. In the NLP distillation space, a practitioner takes an off-the-shelf large model and only does the distillation step. Will there eventually be support for this? And either of you who wants to answer.
Yeah, I mean, I can't, necessarily speak to, whether we might have that in the pipeline in the future, but at the moment, we're primarily focused on model pruning and specifically iterative pruning.
Yeah,
All
and
right.
maybe a good
Yeah.
time to mention too about the transformers, about Hugging Face transformers. Yeah, so me and Ancha actually chose to use DistillBERT for the book, which is a pre-distilled variant of BERT to get the weights down to just above 66 million weights instead of the typical BERT. So yeah, that one's already been pre-distilled, but yeah, I think this question is more specific to the distillation technique for this kind of pruning. Okay, yeah, Ancha, I think that's it. And we are about 10 minutes over time. So yeah, let's wrap it up.
All right. Thanks everyone for joining. And a big thank you to our speakers today, to Eric, Nathalie, and Connor. Really appreciate your presenting today. And I hope everyone enjoyed the session, and hopefully see you next time around. Thanks everyone, and have a good day.